Hello everybody, and welcome to the first of my two talks on the homeomorphism problem for hyperbolic manifolds. Before we start, I want to say a couple of things. Firstly, thank you very much to the organisers for inviting me. This is my first talk that wasn't organised either by myself or by one of my friends. So that's pretty cool. Thanks for that, it's a real honour. The second thing I wanted to say is that these talks are going to be about work that spans 3 papers of varying levels of doneness. The first paper is on the archive and under review. The second paper is finished and on the archive in the next week or 3. And the third paper is a work in progress. I wanted to talk about all 3 of them because they together tell an interesting story. And although, I'm going to be talking about the work of the second and third papers in this first talk, really the big tools that I'm talking about, you can read about them in my first paper. It's on the archive. You could go read about them right now, but maybe wait till after the talks. So let's get started. My talks are going to be focused around the following algorithmic question, the homeomorphism problem for hyperbolic manifolds. So if we ignore this bounded runtime for a second, the homeomorphism problem for hyperbolic manifolds is, does there exist an algorithm where the input is 2 triangulations of finite volume hyperbolic manifolds? What the algorithm does is it tells you whether or not those manifolds are homeomorphic. So there's some things to unpack here. I'm going to require that n be greater than or equal to 3. If n's less than 3, everything's fine still. N is 2, 1, or 0, and those are pretty nice dimensions for hyperbolic manifolds. We understand what's going on there, but the techniques I'm going to be using will require that n be greater than or equal to 3, and that's why it's required here in the question. Triangulations. There's a lot of concepts of triangulation flying around, but for this talk, it's best to think that you're given a simplicial complex. Someone you trust has given you a simplicial complex, and they've told you it happens to be a hyperbolic manifold, but all they've given you is a simplicial complex. Okay, so that's what the question is without bounded runtime. But what does it mean to ask for a bounded runtime version of such an algorithm? There's one concept of bounded. There's a sort of higher concept of bounded runtime about algorithms, a second algorithm telling you how long your first algorithm will take to run, things like that. But really, most of the time what we're going to be talking about is a bound such as this, 2 to the 2 to the 2 to the big OT, where big O means there's some universal constant here. And that bounds either the bits or the number of steps, the runtime of the algorithm. Okay, and in the high dimensional case, we're looking for a similar bound, except that this time you're also going to need it to depend on the dimension as well. But the idea is it depends on the size of the input, t, the number of tetrahedral, the number of instances, and the dimension as well. Okay. So what answers have I got to tell you about? So in theorem form, I can tell you that in the closed 3-dimensional case, the answer is yes, there is a bounded runtime algorithm, and it runs in time bounded by 2 to the 2 to the 2 to the big OT, where t is the number of tetrahedra. And in the high dimensional and cusped cases, my conjecture or work in progress is that the answer is yes again. And this time it depends on n as well. Okay. And these are not 2 different algorithms really. These are, at their essence, they're the same algorithm, but we've gone through and we've changed all the 3's to n's essentially, and we've done all metaphorically. That's what we've done, but we've done all the work to make sure that all the methods still work. But the methods are, in essence, the same, even if they're technically a little more difficult. And so, because of that, throughout the talk, I might make simplifications. I might restrict to a closed case, or I might restrict to a 3-dimensional case, or I might make other simplifications. And I want to assure you that I'm really not hiding something massive from you when I do that. That the core the parts of the argument that excite me, that I think are really powerful, I'm going to try and get those across to you, and the simplifications are simply to help me tell that story. Okay. Now it's important to note there are algorithms which talk about the homeomorphism problem for hyperbolic manifolds, and they think of but they have a different idea of what the input is. And if you change the input of an algorithm, you change the question of whether or not such an algorithm exists. So if the input of the algorithm is rather than just a simplicial complex that happens to be homeomorphic to a hyperbolic manifold, it's a geometric triangulation, for example, where all the simplices are actually geodesic simplices glued together by isometries, then that changes the question, and that could make the question easier or harder to answer. So the input here really it's purely combinatorial. It's a simplicial complex which can be described using a very small amount of data. And it happens to, I said about a friend that you trust earlier, it happens to be there's a promise that a hyperbolic structure exists, that you can believe that, but there's no data about that hyperbolic structure is given to you. There's no hint at how to find that hyperbolic structure, just the promise that it exists. Okay, and so what that means is if I ever talk about geometry, if I ever talk about maybe a representation into the isometry group, or I talk about a geodesic embedding of a simplex or something, those all have to be found by the algorithm. The algorithm that started out with purely combinatorial data has to work its way to finding this geometric information all on its own. That's not something that we give it at the start. Okay. And so the reason that I wanted to talk to you about this work in progress rather than the work that I've just done is that in the three-dimensional case, the fact that the answer is yes is not particularly surprising. The real work here is in getting the bound to be, is in how good the bound is. In the high-dimensional case, the answer, yes, there is a bounded runtime algorithm. That was, to me, surprising. This was a question where on any given day, I might have said yes or no to whether or not there existed a bounded runtime algorithm while I was trying to work this out. It wasn't clear what way the answer was going to come, and so it's quite surprising. And I wanted to, in the second talk, I'm going to talk about the big tools that we're using, how they work. In this first talk, I'm going to try and tell you the story of how I was surprised and why you might find this result surprising yourself. Okay. So there already exist algorithms for hyperbolic manifolds and for the homeomorphism problem. And there are different perspectives you can take here. You can focus on the hyperbolicity of the fundamental group, which we're going to do in this slide. You can look at them as that's the hyperbolic side of hyperbolic manifolds. You can look at the manifold side of hyperbolic manifolds. We're going to have a look at that in the next slide, and we're going to see the limitations of both of these perspectives. So we're going to have a look at hyperbolic groups, and so it's worth noting at this point that there are many algorithmic difficulties in dealing with even finitely presented groups, never mind finitely generated. With finitely presented groups, you can't generally check whether two finite presentations are presentations of the same group. That's the isomorphism problem. That's known to be undecidable. You can't even check whether a presentation represents the trivial group, the triviality problem. That's known to be undecidable. And for large swaths of finitely presented groups, you can't check whether a word in those groups is trivial, never mind the whole thing. So there's lots of algorithmic problems with finitely presented groups, all of which are solved by considering the only Gromov hyperbolic groups. But I just wanted to note this, that just outside these bounds are algorithmic problems lurking, and we're going to see later that those can crop up even when we're dealing with nicer cases. Okay, but you might be wondering, if you've not seen Mostar rigidity before, why are we talking about groups? The fundamental group is not the space itself. But fortunately, in the case of hyperbolic manifolds, they kind of are. So Mostar-Prasad rigidity, proven for closed manifolds by Mostar in 68 and by Prasad in 73 in the cusp case, states that given two finite volume hyperbolic n manifolds, here's one of the places that n greater than or equal to 3 comes in. Their fundamental groups are isomorphic if and only if the manifolds are isometric. So this says comparing the manifolds is sort of equivalent to comparing their fundamental groups. And this already sounds quite strong, but here's a sort of a taste of how strong it is. This sort of regular, general sequence of implications you might be using when dealing with geometric manifolds. The fact that two geometric manifolds are isometric implies that they're homeomorphic. That homeomorphism is in particular a homotopy equivalence, and thus it induces an isomorphism on their fundamental groups. Okay, all of these that you sort of standardly would be using, all of these facts, well, all of these implications, in the case of hyperbolic manifolds, turn out to be equivalences. You can take this whole sequence and send it back the other way. And so if you know simply something about the sort of algebra of the situation, you can understand not only the topology, but the geometry of the situation as well. Okay, and this is why in future talks I might talk about lattices in the isometry group of HN as really encoding all the geometry of a hyperbolic manifold. That's because the fundamental group of hyperbolic manifold completely determines the manifold itself. Thus, the homeomorphism problem for hyperbolic manifolds can be reduced to the isomorphism problem on its fundamental groups. Well, that's great news for us, at least in the closed case, but in fact in both cases, because the isomorphism problem for hyperbolic groups is known to be decidable. So this was proved in the torsion-free case, that's the case we care about, by Solar in 95, and in the torsion case as well, proven by, this was sewn up by Domani and Girardel in 2011. So these two results combine, at least in the closed case, to give a simple algorithm for the homeomorphism problem for hyperbolic manifolds. If you're given two closed hyperbolic manifolds as triangulations, you can look at the two skeleta of those triangulations. That gives you a presentation for both the fundamental groups. Then you can just use this algorithm on their presentations to compare them. And if they're the same, the manifolds have to be the same. If they're different, the manifolds have to be different. And that's it, that's the algorithm. That's an algorithm for the homeomorphism problem for closed hyperbolic manifolds. The fundamental groups of cusp hyperbolic manifolds, note, are not Gromov hyperbolic. However, Domani, again, this time with Groves in 2008, showed that the homeomorphism problem was decidable for cusp hyperbolic manifolds using a very similar solution to what we've seen here. They used a solution to the isomorphism problem for certain relative hyperbolic groups. So the cusp hyperbolic manifolds have relative hyperbolic fundamental groups, and then applied Mostow-Prasad rigidity, much in the same way we're doing here, with a few little tricky intricacies in some cases that we're not going to go into. Okay, so if we don't care about bounded runtime, hyperbolic groups give us the solution. But if we do, well, okay. So as algorithm, there have been no attempts to find a bounded runtime algorithm. And as best as I can tell, the reason for this is that the algorithm is gargantuan. It uses multiple techniques from different areas of geometric group theory. And at no stage does it even attempt to bound its own runtime. There are arguments which prove the existence of constants that bound certain steps, but where there's no attempt is made, because the sort of mathematics that's being used isn't the sort of mathematics that can find that constant and tell you how it depends on the input. And so it would seem that if you wanted a bounded runtime algorithm for the isomorphism problem of hyperbolic groups, you're going to have to find other ways of doing the things that Solar and Domani and Girardel's algorithms do. Okay. Furthermore, here's a result that might scare you away from finding a bounded runtime algorithm. You know, here's a track that doesn't work, and it kind of makes me wonder maybe the other tracks don't work either. So it's well known that any two finite presentations of the same group are related by a sequence of Tietze transformations. And you might think, okay, well, so here's a way that if it worked, you could solve the isomorphism problem for hyperbolic groups in bounded runtime. If you're given two presentations and you have a bound on their complexity, If you could bound the complexity of a sequence of Tietze transformations from one to the other, then here's the algorithm. You just do all sequences of that bounded length from the first presentation. You check what you get at the end, and if your destination presentation is on there, is amongst those, then they must be isomorphic. If it's not, then they must not be. Very simple. So it's simply saying, simply sort of bounding the combinatorial distance between simple presentations of the same group. But, well, I believe it's a well-known theorem that this doesn't work. So given a bound C on the complexity of two finite presentations of a hyperbolic group, there is no computable function. So an algorithm which given C could tell you a bound on the complexity of the sequence. There's no computable function which bounds the minimal complexity of a sequence of Tietze transformations taking one presentation to the other. Okay, so this means you could have two small, not particularly complex presentations of some hyperbolic group, and there's no way, and you can't find, and there's no way you can find a sequence of know how long at least the sequence to get from one to the other is. Okay, so I'm not going to prove this here, but a hint of the proof is that if there were such a function, it could be used to solve the triviality problem of finitely presented groups. And that's known, as I said at the top, to be impossible. And so what's going on here is we're kind of butting up against the problems of finitely presented groups. Okay, so I'll be looking at this, and it seems like, in terms of bounded runtime at least, the hyperbolic group perspective isn't bearing fruit. So what about the manifold perspective? Okay, you see by the title of this slide, okay, at least in higher dimensions, this is a bad place to be. Now, I don't want to spend too long on this because I think these results are well known, but algorithmically speaking, the world of high dimensional manifolds is bleak. And I say here that I compiled some theorems to demonstrate this. This is simply a selection. There are theorem after theorem of simple tasks that you cannot algorithmically perform in high dimensions. And here are just some examples of that. If you forget about hyperbolicity and just try and understand the homeomorphism problem for general n manifolds, as soon as n is 4 or bigger, this is undecidable. All of the problems of finitely presented groups, they appear here and they mess everything up and you can't perform your algorithms. For n greater than or equal to 5, you can't even check whether a manifold is arguably the simplest manifold, the n-sphere. And because in n greater than or equal to 5, you can't check whether something's the n-sphere, in n greater than or equal to 6, one dimension up, you can't check whether things are real manifolds, because to do so, you would have to check whether things were spheres. Okay. And so in summary, both the perspective of hyperbolic groups and, at least in higher dimensions, the perspective of manifolds seem like dead ends for finding a bounded runtime algorithm. Okay, and so that's kind of why the idea that the answer would be yes is quite surprising, because these two natural perspectives don't seem to be useful. Okay, but let's see where we can get a useful perspective from, and it's going to come from a three-dimensional argument that we're going to then take back up to n dimensions. Okay, so in 3 dimensions, things are a lot better. And the main reason for this is this theorem, well, this conjecture by Thurston proved by Perelman, called geometrization. And really this is a sketch of what the result says, but it basically says that if you're given a closed 3-manifold, you can split that 3-manifold up into pieces, all of which have a certain geometric structure. And in particular, some of those pieces, in a lot of cases, are going to be hyperbolic 3-manifolds. And you get closed hyperbolic manifold pieces. You can also get cusped hyperbolic manifold pieces. We call this decomposition the geometric decomposition. Now, Perelman's proof led to many proofs of the homeomorphism problem for 3-manifolds. So without hyperbolicity even being considered, but all closed 3-manifolds, it's known that the homeomorphism problem is decidable. And there's many proofs of this, some more recent using more modern techniques, some even from before the Perelman's proof, sort of taking geometrization as given and then proving it as a corollary. But up until recently, these were all just answering the question of, is it decidable, is it not? And so recently, Kuperberg improved on these algorithms in two ways. Firstly, he gave a bounded runtime algorithm for the first time. And secondly, his bounded runtime algorithm was the first, well, at least that I know of, which instead of using the knowledge of geometrization to prove that some other technique that sort of didn't use geometry would work, Kuperberg's algorithm implements, makes effective this geometrization. The algorithm actually cuts the manifolds up into pieces and then compares the pieces, taking advantage of their geometry. Okay. So what that means is that Kuperberg has to come up with an algorithm to compare the hyperbolic pieces. So let's state this more formally. Kuperberg shows that there is an algorithm which, given two triangulations of closed three manifolds, checks whether or not they're homeomorphic, and it does so in time bounded by a function of the number of tetrahedra in each of the triangulations. In particular, the algorithm contains within it, as I was just saying, a bounded runtime algorithm to answer the same question of finite volume hyperbolic three manifolds. One snag in Kuperberg's algorithm is that the bound is of the following sort of unknowable form. It's 2 to the 2 to the 2 to the 2 to the t, where this dot 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 means we don't know how high this tower of exponentials is. We know it's bound is some unknown universal constant, but we've no idea how tall the tower is. And the way that this comes about is that if you have this complexity class, it's called ER, or elementary recursive. If you have a bunch of algorithms that all lie in this class, and you combine them, you find some way to sort of integrate one algorithm into the other, then their combination will also lie in this class. And also what it means is that what Kuperberg can do when proving this algorithm is he can show, without going into too many details, he can show that something lies in this class, and then he doesn't have to work out how tall the tower is, doesn't have to go through all those details to work out how tall the tower is. And so for an algorithm like Kuperberg, which combines like 10 different algorithms for cutting up and then comparing all the pieces, this makes a lot of sense as a bound, but it leaves open the question, how tall is that tower? And really that was the question that I sought out, at least in the hyperbolic case, to try and answer. And that's where this idea for the higher dimensional stuff came from as well, is trying to optimize Kuperberg's hyperbolic sub-algorithm. So how does that hyperbolic sub-algorithm work? Well, it's two steps. First, you find a geometric structure on each manifold. So this means you're given just combinatorial information, what I call a topological triangulation, and you construct from it a geometric triangulation. Now, the way this is done, if you just have you just know there's a homeomorphism from your triangulation to the manifold, then the edges might be all wobbly, the whole thing might be, and you straighten that out to make a geometric something. Now, it turns out that straightening everything out breaks the fact that it's a triangulation, so you have to fiddle around to make it actually a triangulation again. That can be done, and we'll talk more about that in the second talk. The second thing you do now that you have this geometric triangulation is you compare the geometric triangulations. So I've written a little blurb about how that works, but essentially we're just going to rely on the good work that's already been done by someone else. So Kolelka and Fanza, in work that's going to be published later this year, I believe, showed that for closed hyperbolic N manifolds, there's a bound on the runtime of an algorithm comparing two geometric triangulations. Now, I mentioned this before, sometimes the input comes with extra information. So in their case, that it's a geometric triangulation rather than it's just a topological one. And even more, their input requires you have some understanding of the complexity of the geometry. So they're bound as a function of the number of n simplices, the dimension, but also this geometry. We called it G, but you can think of G as something like the maximal length of an edge in the triangulation, the volume times by the volume of the manifold divided by the injectivity radius, something like that. And their algorithm has runtime bounded in the following way: 2 to the 2 to the big O, and then it depends on NCNGT. But that's very approximate. That's not how they word their solution. And so what we need to do to be able to use curl fans as a result is we need to be able to find a geometric triangulation. And we need to, well, the dimension is going to stay the same. We need to control the number of n simplices that geometric triangulation has. And this is the part I'm really excited about. We need to control the geometry of the hyperbolic manifold given only combinatorial information. Okay, so that's what we're going to be talking about next time, is given a topological triangulation, how to get control over its geometry. And that's what I'm really excited about. And so I hope you can see that. Thank you.